Hello, everyone, and welcome to the next lecture in the reinforcement learning phase of our course Reasoning LLMs from Scratch. In the last lecture, we covered the concept of Markov property and we looked at how reinforcement learning problems can be described as a Markov decision process. In particular, a state signal has a Markov property if it retains all the relevant information from the past. And then, whichever reinforcement learning problems in which the state signals have a Markov property are called as Markov decision processes. In today's lecture, we will build upon the concept of Markov decision processes and we will discuss a very important concept which is called as a value function. In my study of reinforcement learning, I have come to understand that the importance of understanding the concept of value function is at the heart of understanding all reinforcement learning type of problems. And even in the large language models like DeepSeek, for example, whichever models are using reinforcement learning for improving their LLMs, to understand how that improvement is happening, understanding of the concept of a value function is extremely critical. And that's why we are going to have a very separate lecture today on value functions. I have not clubbed it with any other concept. So let us start to understand what is the meaning of a value function. Remember, in the first lecture of reinforcement learning, we said that what is the meaning of value? In fact, values was one of the four elements of reinforcement learning type of problems. And then in the first lecture, we also said that the meaning of value is not the immediate reward which the agent receives, but the cumulative expected reward in the long run. And there is a very nice analogy that we gave to understand values. Imagine that a team has chosen a player for a tournament. Let's say it's a game of cricket, and there are 14 matches in that tournament. And let us assume that in the first two matches, the player does not play well at all. Now, as a team management, they are invested in the or they are more concerned about the value of this player. They believe that even if this player has not performed well in two matches, the value of the player is high, which means that eventually the player will deliver in some of the upcoming matches. Which means that if you add up all his scores over the 14 matches, it will add up to a good value. So we can neglect the first two matches. So value means the cumulative reward which the agent receives in the long run. Uh, And this is similar to the concept of expected return, which we looked at in the last lecture. Remember, we saw what is our expected return and how it is different from individual rewards. So let's look at a state value function. A state value function is, let's say, we start from this state, right? And then we jump from this state to this state, and then again we jump from this state to this state, and so on. The value of this state is not the immediate reward which I receive over here, but the addition of all the rewards which my agent receives in the future. So basically you sum up all the rewards, and then you ask the question, okay, what is the expected value of this sum, of this cumulative sum in the long run? And then you will get what is the value of this state. Okay, so the state value function is denoted by this symbol, which is called as v subscript pi of s. This means that we are calculating the value of this state s when the agent follows a policy pi. we are going to stay consistent with this notation v pi of s. Actually, you can pause here and you can write down the uh, expression for v pi of s simply based on the discussion on expected return we had in the last lecture. So just pause this video, take some time to see if you are able to come up with an expression for this. If not, let's try to understand it together. So the formula for the state value function is given as follows. V pi of s is equal to, uh, okay, before I go that, let's try to understand it without looking at the formula. So remember we saw that g of t is the expected return, and then what was this expected return? This was rt plus 1 plus gamma times rt plus 2 plus dot dot dot, where gamma is the discount rate. Uh, and this formulation we saw is especially suitable for tasks which are continuous, not episodic tasks, but nevertheless, we will look at this formulation of the expected return itself. So now this is the expected return, and what I'm trying to say is that I'm trying to find what is the expected value of this. So what I do is I simply put a e before, and then I say what is the expected value of g of t given my state is s. Let's see if that's correct or not. Yes, that's correct. But then I missed one symbol at the bottom, which means that the agent is following the policy pi. Okay, and then after you write this, you simply sum up g of t, where you say that it's this expression simply, which means that it's going to be sigma k goes from 0 to infinity, gamma raised to k r of t plus k plus 1. Try to expand this by yourself. You will see that you will exactly land up with this expression. Okay, so this is the expression for v pi of s. Don't get too bothered by the mathematics. The intuition behind the value of a state is straightforward. Essentially, what we are doing is that we are seeing that if an agent is in one state s, then what are the possible future rewards that it will get in the future, and then we say that okay, if you sum up all these rewards, what is the expected value of the entire sum of the rewards. And then we have a discount rate there, because we are saying that future rewards are not as valuable as immediate rewards. Remember the discussion we had where we said that if you have a 100 rupee note, then the value of this 100 rupee note 5 years later is much less compared to the value of this 100 rupee note right now. And the concept here is very much similar. We are saying that rewards which are more immediate are more valuable compared to rewards which you receive in the future. And this intuition is incorporated very nicely in the discount rate, which is denoted by gamma. Okay, so this is the value of the state, or this is the formula for the state value function. Okay, let us move ahead. After we have discussed what is the state value function, we have to now go ahead and we have to look at what is the action value function. Okay, so the action value function means that we are still calculating the expected return from a state, but the only difference as compared to a state value function is that here we are calculating the expected return after the agent takes an action and then follows the policy pi. So the main difference between the state value function and the action value function is that, let's say you have got an agent which has reached the state s, okay, or which has received a state s from the environment, And then you ask the question that, okay, what is the value of this state? That is given by the state value function. And now let's say from this state S, you have multiple actions that you can take, right? And all of these actions are going to have a different value of the expected return for their path. For example, if I follow this path, I will have an expected return. If I follow this path, I will have another expected return. If I follow this path, I will have another expected return. So, what action value function answers is that if I give you state and I also give you the action which the agent follows after reaching that state, then can you tell me what is the expected return in the long run for this agent? That is the meaning of a action value function. The only difference is that we are not just starting from one state right now, but we are also giving the action which the agent has taken. So the action value function is denoted by this formula, where the symbol q is used to denote the action value function. And again we have the subscript here which is denoted as pi. But here you can see the action value function has two parameters which is different than the state value function which only had the state s. Along with the state s, now we also have the action a which is taken by the agent. So the action value function depends not only on the state of the agent but also on the action which the agent takes. Now, can you pause over here and try to think what would be the formula for the action value function? You can pause here and try to see if you can get it for yourself, and then we'll try to look at it. The only difference that we are going to make over here is that again we are going to calculate the expected value of the summation of all the returns from this state. But then what we are given is st is equal to s, and we are also given at is equal to a. This is the information that we are given, so that's the only difference which we make in the formula. Other than that, this formula is exactly similar as compared to the formula that we have for the state value function. So this is the formula which we have for the expected value, for the action value function, where e denotes the expected value. We are going to use the concept of state value function and action value function multiple times in the reinforcement learning phase. So we are going to try to develop a more finer intuition of these concepts as we go along through to the remainder of the course. Now, there is a formula which we can derive for the state value function, and here the formula is like this, right? But it turns out that if you use the uh, property of the state signal having a Markov property, then you can simplify this derivation and you can appear at a version of, or you can appear at a formula for the value function which looks like this. Uh, so let me explain what this equation means. This is called as the Bellman equation, and the Bellman equation is used to estimate the value function of a state. In other words, it is used to estimate the state value function. And I have attached a note in the description of the video where the derivation of the Bellman equation is given, but I believe that the derivation is not crucial for us to build an intuitive understanding of what exactly is happening over here. So let's try to understand what the Bellman equation says by building an intuition for this particular example. So let's say that we are starting at state S. This is where the agent starts. And from this state S, the agent can take multiple actions. Uh, Let me denote these actions like this. So this is one action, this is second action, and this is the third action. Let me denote these actions by A1, A2, and A3. And then after the agent takes these actions, the agent will go into the next state and also receive a reward. So let's say from here the agent can go to these states. From here the agent can go to this state, and then after the agent takes this action, the agent can go to these states. Okay, so let's say this is uh, the diagram that that we have right now. So these states, so this is the present state of the agent, and these states, let us call them S dash. So these are S1, S2, S3, S4, and S5. So there are five different possible states which the agent can go into in the next time step. Now, uh, conceptually, what the Bellman equation says is that the value function of the state S is or can be expressed in terms of the value function of S dash. And this is the main intuition which the Bellman equation offers us. It says that the value function of the present state can be written in terms of the value function of the next possible states in which the agent can be in. Uh, okay, so let's try to understand how that can be written. So firstly, let us look at one term in which we can understand the first factor of the Bellman equation. Okay, so you can see that there are how many paths in this diagram. This is path number one, this is path number two, this is path number three, this is path number four, and this is path number five. Okay, and then there are going to be rewards which are collected along these paths. Now, let us focus our attention on one single path, which is the path on the extreme right. Now, what the Bellman equation says is that the value function of this state is going to depend on the value function of the next state, but it has to be discounted by a factor of gamma. So, it's going to be gamma times v of s dash, and then you also have to add a reward along the way. So you add a reward along the way and you discount the value function of the next state, and then you also have to multiply it by the probability that the agent can go into that state. So for example, here we have to write probability of s dash comma r given s comma a. Remember, this is the transition probability which we discussed in the last lecture. So this is the transition probability. uh, this is the reward which the agent collects along the way. This is the discount rate, and this is the value function of the next state, value function for the next state. And then all of this you again have to multiply by what's the probability that the agent is going to take that action in the first place. So which is pi of a given s, and then you just sum it up for uh, possible next states and rewards for all possible s dash comma r. Let's see if the formula which I have written is correct. Um okay, so there are two summations over here. There is one summation outside and there is one summation inside. Okay, so let me make that correction. So there is one summation which happens for all s dash comma r, and then there is one summation which happens for all actions. So let me again explain what we are doing over here. Essentially, what we are saying is that the value function of one state is heavily influenced by the value function of the next states. But we don't just write the value function as the summation of all possible next states. But what we do is that we discount the states by their values and we add a reward which the agent gets along the path. And then we add two other terms. The first term is what is the probability that the agent is going to end up in this state, and that's given by the transition probability of s dash comma r given s comma a. And then what's the probability that the or what's the probability that the agent is going to select this action in the first place. So this is given by the policy. So remember, pi is our policy. So this is the Bellman equation, which gives us some kind of a mathematical uh, means of describing the value function, and it's only possible because we have assumed that our state signal has the Markov property. Now we are going to understand this equation again, but in terms of uh, an actual practical example so that you understand how the Bellman equation is used in theory. Okay, so we assume that this is the scenario. The agent is present, or the agent has received state S from the environment, and now the agent can take three possible actions: A1, A2, or A3. And then after it takes those actions, it can transition into multiple states. So there are six states overall which the agent can now transition into. Now what we want to do is that we want to find the value function of the state S in terms of the value function of all of these possible states. So let's see how we can do that. So there are six possible future states which are denoted by S1 to S6, and the rewards for these six possible states are denoted by R1 to R6. So here this is R1, this is R2, and then this is R. Oh no, this is reverse. This is R1, this is R2, and then dot dot dot, this is R6. Okay, so now let us use the Bellman equation to find out how we can express the value function of this state in terms of the value function of all other states. So the first term is going to be for this path, and then what we'll do is we will simply take the reward, discount it with the value of that state, then we'll multiply it by the transition probability s1 comma r given s comma a, and then we'll multiply it by the policy. Okay, let's see. So this is exactly what we do here. This is the policy which dictates what's the probability that this action is taken when the agent is in this state. This is the transition probability. What's the probability that the agent transitions from state S to S1? But the main intuition is embedded over here, which says that the value function is the reward collected along the way plus the discounted value function of the next state. And we apply the same logic to all of these six terms. You can see that in these first two terms, the action is the same. So here A1 stays as A1, but then the state changes and the reward also changes. So we have six terms, and the value function is going to be an addition of all of these six terms. Remember from the recycling robot example that we actually have values of all of this. So we can actually substitute those values of the transition probabilities, and we can actually get an equation for the value function of one state as a function of the value function of all the other states that follow that particular state. And okay, so this particular diagram that we have used is called as a backup diagram. The backup diagram shows the link between one state, the possible future states, uh, the possible actions from one state, etc. So it's like a visual way of representing how the agent is interacting with the environment. So to summarize, the Bellman equation allows us to calculate the value function of state S by saying that the value of the start state equals the discounted value of the next state plus the reward which the agent collects along the way. Okay, now the question that we try to answer is that we have seen now a state value function and we have seen action value function as well. And we have seen how the Bellman equation can be used to write down expressions which express the value of a state as a function of the value of the immediate next states which the agent encounters. Now we are going to understand what is the meaning of an optimal policy. Remember, the whole goal of even expressing these kind of problems as an agent environment interface, assuming the state signal to have the Markov property and writing down the equations for value function in terms of the Bellman equation. The whole point of doing all of this is to find out what is the optimal policy for my agent. In other words, given a state, what is the best action for that agent in that particular state? So let us see the meaning of an optimal policy. A policy pi is better than a policy pi dash if its expected return is greater than or equal to pi dash for all the states. So basically, if I have a policy, right, and it's giving me a certain value for all states, and then if you tell me that Rajat, I have another policy which is giving good values at some states but not good values for other states, then I cannot say with confidence that your policy is better than mine. But if you come to me and say that Rajat, I have got a policy which gives me higher values of for the states for all the possible states which the agent encounters, then I will replace my policy with your policy because your policy is better than my policy. So here we define the optimal state value function as v star of s, where v star of s is equal to maximum of, basically we find a policy which maximizes the value function for all the states. And optimal policies also share the same optimal value function, which means that if my policy is optimal, uh, then I am going to also take actions whenever I am in a state that maximizes the expected return after being in that state and taking that particular action, which is also represented by the action value function. So we define the action value function which is optimal as q star of s comma a, which is finding which is for an optimal policy, the finding a policy which maximizes the action value function for all the states and the actions which are taken from that particular state. Now the question is that how do we find these optimal value functions? Can we somehow use the intuition that we built previously to check whether the value function that we have got is optimal or not? How can we do that? So let's try to see. Okay, so let us say this is our state, right? And what I want to do is, let's say from this state, there are multiple possible actions. So A1, A2, A3, A4. So if my policy is optimal, then what it means is that I am going to select. So this is A1, A2, A3, and A4. If my policy is optimal, then I will select an action which maximizes the total expected reward along that action, right? I will not select an action which gives me a less expected return if I take that action. So, in other words, what we are trying to do is that we are trying to maximize uh, the action value function. We are trying to find actions which maximizes the action value function for every state. Uh, this is what I think of logically. If I do this, and if I do this for all possible states, then whatever policy I get has to be optimal because I'm choosing actions that give me the highest expected reward at every possible state. So, as far as my intuition tells me, I have to do something like this. Let's see what is the case actually. So, the value function will be optimal if for each state the action which yields the maximum expected return is chosen, and this can be expressed as something like this: v star of s is equal to maximum of uh, the action value function q pi star s comma a, and the maximum is performed over all the possible actions, which means that this is quite similar to what we had written over here. We are trying to find actions which maximize uh, the action value function and the value of the action value function. And we are saying that if you are trying to maximize this, it means that you are finding a policy which is maximizing your action value function, which in turn means that you are finding a policy which also maximizes your state value function. And after we expand this equation, what we get is we get the following equation. So this equation is called as the Bellman Optimality Equation, and it directly follows from what we have written over here. So let us again develop an intuition for this term so that we understand it properly. What we are saying is that if I am at state S and I have multiple options, multiple actions which I can take from this state. So usually when I write down my value function for this state, I am calculating an expected reward which I get when my agent is in this state and it follows a particular policy. And what we are saying is that if the policy is optimal, then whatever value the optimal policy gives as the value of this state is going to exactly match the value that you get by doing this operation, which is maximum of q pi of s comma a. So what I'm doing over here is that I am choosing actions. I'm choosing an action which gives the maximum value for the action value function, which means that I'm choosing an action which gives me the maximum expected return in the long run. And if my policy is optimal, then my value function will also give me the exact same value, because whatever action will be followed by my value function will be exactly same as the action will be chosen by doing this maximum. In reality, v pi of s, which is the value function for a specific state, and action value function, which is the value of this expression when you take an action, there is no reason for both of these to be equal, because this action can be anything. It might not be. So let's say there is a1, a2, a3 and a4, and your policy tells you to take action a1, but here I might have a2, a3 or a4. But if the policy is optimal, then here my agent will choose an action which maximizes this, which is what we are writing in this expression. And if you expand this, you will get an equation which looks like this. This equation says that the optimal value function for a specific state is again dependent on the optimal value functions for the next possible state. But remember, there is one specific term here which is missing than the Bellman equation which we saw before, and that term is pi of a given s. And the reason this term is missing is because we are calculating an action which gives us the maximum expected return. Again, if we take the same example which we took to understand Bellman equation better, let's say we have a state S over here. From this state, you have three possible actions. And then let's say there are these possible next states. So let's say this is S, and all these possible next states are represented by S dash. Now, what we are saying in this Bellman optimality equation is that for all the paths which you see in this backup diagram, for all of these paths, this is first path, second path, third path, and fourth path. For all of these paths, you uh, calculate this value, which is the expected reward that you get along this path, plus the discounted value of the next state, v pi of s dash. And then what you do is that you multiply it by the transition probability of s dash comma r given s comma a, and then you find an action that gives you the maximum of this. So there are these three possible actions. Now, here in this expression, unlike the previous expression where we added all this, there were six terms, remember, which we added. In the Bellman optimality equation, we are not adding all these terms together, but we are only choosing one single action that is going to give us the maximum expected value for this state. And we are going to find out that action by understanding out of all these actions which action is giving us the maximum for this expression. So that is what is given over here. We are finding out an action which gives us the maximum value for this state. So essentially, the Bellman equation is the Bellman equation which we saw previously, we were adding uh, the return plus the discounted next value for all of these paths. But in the optimality equation, you don't add the values you get for all the paths, but you only choose that path which gives you the maximum reward along the way plus the discounted rate of the value of the next state. So, this is what the Bellman optimality equation says. Now, the question is, let's try to see how we can calculate it, uh, calculate the optimal value function of state S, which is shown in this diagram. We have three actions here. So we have to choose the action which gives the maximum expected reward. So this should be return, actually, maximum expected return. And to calculate that, what we do is that we calculate expressions, this expression for all of three actions. So for the first action, we have this. For the second action, we have this. And for the third action, we have this. Now we are going to take whichever value is maximum among these. And we are going to only use that term and say that the value function is going to be the maximum value of, or that value which is maximum out of all these three terms. So this is the Bellman optimality equation, where it is in a way quite similar to the Bellman equation, but the only difference is that in the Bellman equation we added up the values given by all the paths, but here we don't add up the values given by all the paths. But what we do is that we take the path which gives us the maximum expected reward plus the discounted value of the next state which the agent encounters. Now, what we'll do is that we will try to see how we can calculate the uh, or how we can solve the Bellman optimality equations for a very practical example. And the practical example that we are taking over here is that of a recycling robot. We are going to see how the Bellman optimality equation can be solved, uh, and how we can find the maximum expected value for this particular problem. Now, remember what was this problem? What we saw was we had a robot which was tasked to pick up as many trash cans as possible. And there were only two states for this robot, either high or low. And for each state, the robot could take different actions. There were three possible actions: either the robot can actively search, the robot can wait, or the robot can go back to the charging station and recharge itself. We are giving a reward of -3 if the robot has to be recovered and the battery dies. Otherwise, we are giving a reward of R search, where the robot is actively searching. If the robot waits, someone else puts the cans, then we give a reward of R wait, where R search is greater than R wait. And this is the table that we saw. Let's take one example. If the robot is in the high state and performs an action of searching and stays in the high state, then the reward that the robot gets is R search. But if the state becomes low, then also the reward gets R search, but the probability is 1 minus alpha. If the robot has a battery level of low and still stays low, then the reward is R search. But if it's searching and the battery dies down, it has to be recovered. So the next state becomes high, but the reward that the robot gets is very low. And then the other cases are, if the battery is high, the robot is waiting, then of course the battery will still stay high with a probability of 1, but the rewards are much less compared to our search because the robot is not actively searching. Very similar logic for this case also. And the last case is when the robot decides that it has to go back to the battery station and recharge itself. So the battery switches from low to high, and the reward the robot gets is zero because it's not collecting any trash at this stage. So to write down the Bellman optimality equation, we first draw the backup diagrams. One backup diagram is for the high state, and one backup diagram is for the low state. If the robot is in a high state, the robot can either search or wait. If the robot searches, the next state can be either high or low. Similarly, for wait, the next state can be high or low. But if the state is low, we have three options. We have either search, the robot can either wait, or the robot can recharge. And for all of these three actions, the next state can be high, low, or high, low. So overall, we have four cases over here and we have six cases over here. Now the question is that can we use the Bellman optimality equation to find out what is the uh, maximum expected return for both the states, for the high state as well as for the low state. Now let us see. So firstly, let's look at the Bellman optimality equation now. So we have to use this. V star is equal to maximum of these terms. So for the high state, there will be two terms because there are uh, two actions which the agent can take, and we have to take the maximum of these two actions. Remember how to find the optimal policy? We have to choose the action which yields the maximum value for uh, the action value function. So that's why we have to take the maximum of two terms. First term is for this action, second term is for this action. Now when you expand these terms, let's see how we can expand it. So first let's look at the inner bracket. Here we have the reward collected along this pathway. This reward is collected along this pathway, and plus discounted value of this state. And then here we have the reward collected along this pathway plus the discounted value of this state. And then the only thing we do is we multiply the probability of the agent reaching this state from this state. So you can see these probabilities multiplied on the left. And term 2 is very similar, but we have this other half of the diagram. And here also the inner bracket is the reward collected along the way plus gamma times the value of this state, and the second term is the reward collected along this path plus gamma times the value of this state. And then again we are multiplying that with the probability of the agent reaching that state from the high state. Similarly, we can write three terms for low because we have three actions and we have to choose which action gives us the maximum reward. And then there are these three terms which are again very similar to what we discussed before. I want you to pause at this step and try to see how these steps are derived, because then you will understand the Bellman optimality equation and the terms more clearly, and you will get more confidence to use these equations as well. And now what we do is that we substitute the values of these rewards and these probabilities, and we actually solve these equations. So I have given the code in the comments. You can run the code. It's a simple code. It runs quickly, and you can see that the maximum value that we get for high and low is 25 and 22. So as the iterations proceed, you can see that the value functions converge, and the optimal value for the high state, which is v star of high, is 25.42, and v star of low is equal to 22.88. Now one thing which I have not given here is that what is the optimal policy. In other words, if the robot is high, what it should do; if the robot is low, then what it should do. So the code also will give the optimal policy, but I want you to comment in the comment section what is the optimal policy. whether it's search or wait for high state, or it's search or wait or recharge for low. It will be one of the two for high, and it will be one of the three for low. Okay, so this brings us to the end of today's lecture. Overall, in this lecture, we saw what is the meaning of value function. A state value function is the total expected return the agent receives from that state into the future. And the action value function is the total expected return the agent receives from that state into the future after the agent takes a specific action. And then we understood how we can use or write the value functions in terms of the Bellman equation, which says that the value function of this state can be written as, or can be written in terms of the value function of the next possible states, discounted by the discount rate, and adding the reward collected along the way. But to find the optimal value function, we don't have to choose all the pathways. We only have to choose one pathway which gives the maximum value of the reward collected along that pathway plus the discounted value of the state, of the next state. And we looked at an intuition for this where we saw that if the policy is optimal, then uh, to find that optimum policy, what we have to do is that we have to find the action from each state which gives the maximum value for the action value function for that state. And then after you expand this equation, you get the Bellman optimality equation, which gives you the best policy which you can use to select your actions. And this is one of the very cleanest algorithm, because we are simply using mathematics to solve these Bellman optimality equations. There is no uh, I would say interaction of the agent with the environment. It's like we already know the model of the environment beforehand, and we are using the model of the environment to uh, simplify the problem and to analyze the problem only using mathematical equations. So this is one of the clean and simple uh, methods which you can use to solve reinforcement learning problems and to find optimal policies by simply using the Bellman optimality equation. Thank you very much, everyone, and we'll see you again in the next lecture.